Okay, welcome to Note Set 13, where we're going to talk about transposes and permutations. This is coming out of section 2.7 in your textbook, and with this note set we'll be finishing off chapter 2. So this is kind of a catch-all at the end of this chapter, primarily intending to formalize this idea of transpose. I had briefly mentioned it in an earlier note set, but here we formally introduce it. We've talked about permutations before, but we'll talk about them here in the context of transposes, permutations, inverses, and how this all fits together with the LU or LDU decomposition. So we've previously discussed the idea of the inverse. So you give me a matrix, or I give you a matrix, probably more likely, and ask you to find the inverse of that if it's invertible. So that's finding from one given matrix, find another one that has a certain characteristic. In that case, that is the inverse of that. Well, now we're going to talk about something called the transpose, which is a little bit different. Every matrix has a transpose, unlike the inverse, where some matrices have an inverse, some matrices don't. Every matrix has the transpose, and so it's a simple operation that you apply, and basically you just say, well, what were the rows of A become the columns of A transpose. And we use this superscript T to indicate transpose. So here's an example. So we've got A is equal to this matrix. If we say, well, here's the first row is 1, 2, 3, the first column of A transpose will be 1, 2, 3. Second row of A is 0, 0, 0, so the second column of A transpose is 0, 0, 0. Notice that this was a 2 by 3 matrix, and the transpose becomes a 3 by 2 matrix. So the transpose interchanges the number of rows and columns. So another way to think about this, and let me get rid of the ink here. Another way to think about this is that the matrix flips over its main diagonal. So if we draw a main diagonal, so the main diagonal always starts at the upper left corner, and we just draw a line down, however far down we need to go for the given matrix, where we're just going, over 1, down 1, over 1, down 1, over 1, down 1. That's what we mean by the main diagonal. Let me get rid of that ink. Come on, there we go. So if we draw this line and then think about anchoring here and here and flipping it, so those two elements stay in position, and this one goes up there, those two interchange, and you can kind of think about it as taking a piece of cardboard, putting a pencil through those, holding on to the ends of the pencil and flipping. So that's the basic idea. Another way to think about this is that the entry in row I, column J of A transpose comes from row J, column I. So note that we have row I in row J, column J, and column I. Another way to say that is that the ijth element of A transpose is the ji element of A. So there's an illustration for this given matrix. Here's the A13 element, and that becomes the 3-1 element of the transpose. So some rules for transposes, just like we had some rules for inverses. Now, we did not have a rule for the inverse of the sum of two matrices, but we do have a rule for the transpose, and I think it's pretty easy that you can imagine that this does hold. So the transpose of the sum is the sum of the individual transposes. The product works sort of like the transpose rule for products works sort of like the inverse rule for product. So transpose of AB becomes B transpose A transpose, and the order reverses. It's a little harder to see why that is the case for transposes than it is for inverses. Remember, for inverses we had the idea of socks on, shoes off, socks off. But it's a little harder to see that here, but it does have to work that way. So here's the way that we can see why that happens. So remember that A times X, this X folds over and combines the columns of A. Well, let's look at what if we took the transpose of the whole thing. So the transpose of quantity AX, according to our rule up here, will be interchange the order and transpose both. So this now, again, using our view from matrix multiplication, what this will do is combine the rows of this. And so, but remember, the rows of this are the columns of A. So this operation does exactly the same thing as this. The first combines the columns of A, the second combines the columns, or the rows of A transpose, but the rows of A transpose are the columns of A, so everything works. And so then we can just use that idea to extend to this. If we have A times B, and we say that B is made up of columns x1, x2, and so on, we can pass the A through into each column, and so then if we apply the transpose to that whole thing, we would get something that looks like this. And because these are this is the first column of the result, so we would want to convert that into the row of it. That would mean we would transpose it. So this transpose would become the first row, but we've already established here that we have to interchange the order for that form. And then we list them all, just like we should, and then we can interpret that to be B transpose times A transpose. So we've, in a sense, proved this result, although not formally. Here's an illustration, A times B. Here's B transpose times A transpose, and we can see that the results are in fact transposes of each other. So this reversing the order rule can be used for any number of matrices that are being multiplied. So if you've got ABC, quantity transpose, you reverse the order C transpose times B transpose times A transpose. So let's remember the factorization that we did, LDU. So you give me an A, we can factor it into LDU. Well, if I take the transpose of A, I'm going to do the U transpose. Remember, everything gets reversed. D is in the middle, so it stays where it was, but also transposed. L transposed. Now remember, D is diagonal, so you can verify, and it's not terribly difficult to even just visualize this in your head. Diagonal matrix is its own transpose. So we can replace D transpose by D. And so also remember that U transpose will become a lower triangular matrix, and L transpose will become an upper triangular matrix. So just transposing the LDU gives us, following this rule needs to be true in order for that to just convert into an appropriate LDU decomposition for the transpose. So what about if we're doing inverses and transpose? Well, the rule is if we transpose an inverse, it's the same as doing the transpose first and then doing the inverse after that. And we can easily verify that. So we've got A inverse must give us the identity matrix. And so now if we apply a transpose to both sides of this, I'll put a transpose here, put a transpose there. Well, I transposed is just I. That's pretty easy to see. And if we apply our rule here, we'll need to apply. Do I have this backwards? Yeah, I think I got this backwards. I need to put this the other way around. So it gets transposed to, this should be in here, I think, is what I'm trying to do. So A transpose is invertible exactly when A is invertible. So this thing becomes the inverse of A transpose. So here's an example. I've got this matrix, and here's its inverse. Hey, we should know how to do that. That's nothing more than an elimination matrix, and we know that the inverse of an elimination matrix, you just change the sign on that. So what is, this really should, I think, say A transpose inverse. Well, there's A transpose. A inverse transpose is just the transpose of the inverse, but we can also verify that it is the inverse of the transpose itself. So you can verify that easily enough. And this allows us to think about the meaning of inner products. So we defined an inner product earlier in the course, and I gave you two different notations. One was with was using a dot to be a dot product, and then I also said there's a way to write it with the brackets like this. So those are two different ways to write inner product. But there's now, armed with transpose, there's another way to write that inner product. So we can verify that this ends up giving us exactly the result that we get for the inner product or the dot product. And so you can see a way to remember this. When the transpose is inside, we get the inner product. And this is just showing how those interact. So X and Y are both n-dimensional vectors, so X transpose is going to be 1 by n, whereas Y is n by 1. So the inside dimensions match, so we can do this multiplication, and the outside dimensions give us 1 by 1, so this thing ends up giving us a 1 by 1, or a scalar, which is exactly what a dot product or inner product gives us. Now, when the transpose is outside, then we do something like this. X times Y transpose. The transpose is outside of the product, and so this is called an outer product. And again, we can see that for X and Y both being n-dimensional vectors, this operation is valid. So we've got X, which is n by 1. We've got Y transpose, which is 1 by n. So the inner dimensions match, and the outer dimensions give us an n by n. So the inner product gives us a scalar, and the outer product gives us a matrix. So here are some examples of inner products. So the outer product shows up every once in a while, but the inner product is really a workhorse in linear algebra and also in all sorts of areas of electrical and computer engineering. So, and other types of engineering as well. So if we had a vector that held movements, some measurements of movements, and we had a vector that was corresponding to the forces. If you remember, work is equal to the movement times force. We can do an inner product X transpose times F. Similarly, in circuits, we have a bunch of different voltage drops and their corresponding currents. And so if we do all those different voltage drops times their corresponding currents and add them all up, we get the total. Well, it's labeled here as heat loss, but heat loss is just power. And in other areas like economics, we have quantities times prices would be equal to the amount of revenue or income. So this idea of inner product, I tell you, it's everywhere in engineering. When you get into your higher level EE and COE courses, even if you're not being told this is an inner product, they're in there all over the place. Now we gave a rather simplistic definition for a transpose, and this just comes out of looking at matrices and saying, hey, gee, sometimes I need that other shape. But really, mathematicians discovered that there's a more intrinsic way of defining what the transpose is that kind of comes from a deeper part of mathematics. We don't really need to know why they did this or where it really comes from, but it's worth knowing that mathematicians kind of define it this way. So mathematicians say that the process of transposing a matrix, this new matrix A transpose, should be exactly the matrix that makes the following two things defined in terms of inner products equal to each other. So if we take AX and then transpose that, and then that gives me a vector, what I'm really doing is doing the inner product of AX with Y, and on the other side I'm doing an inner product of X with this new thing, A transpose, operating on Y. And so mathematicians say we defined the transpose of a matrix as precisely that matrix that makes this happen. And again, don't worry why they did that, but they did that. And so let's see, at least from an example, that this is completely consistent with our first definition of what transpose means. So here's a matrix A. Here's a vector, three-dimensional vector X and a two-dimensional Y. So if we first do A operating on X, so A operates on X, so this is a 2 by 3, this is a 3 by 1, so we can multiply A times X, and what do I get? Well, I get a 2 by 1. So I have a 2 by 1 in here, which after the transpose gives me a 1 by 2, which I can multiply with a 2 by 1. So that works. And if we work it out, here is the result of A having operated on X. So we get these two elements. And then if we work that out, we get something that looks like this. So it's going to be x2 minus 1 times y, that's this first term, then x3 minus 2 times y2, that's the second term, and we add them all up. Now let's just do a little bit of algebra and manipulate this around. That can be rewritten as just get all the x1s together, get all the x2s together, and get all the x3s together. And so there's all the x1s together. There's really only one of them. Here's all the x2s together, and we just come up with a common thing that multiplies x2, and then we got our x3 term. Well, so that looks like setting up the x transpose, right? Because we've got an x1, x2, x3 inner product with a vector that looks like it has these three elements. So x transpose with A transpose Y. So those three elements must be the result of this. So this is just, well, it's not X, it's X transpose multiplying A transpose Y. And so therefore we can figure out what this result must be. So A transpose Y must have this as its first element, must have this as its second element, and must have this as its third element. And if we puzzle it out, we can figure out, putting a -1, 0 there gives me the negative y1. Putting a 1 and a negative 1 gives me the y minus y2. And just putting a 0 and a 1 here gives us the y2. Now, if you can't see this real quick, you haven't practiced matrix times vector multiplication enough. So, like I said earlier, you got to have this down pat so that it just becomes second nature at this point. So please practice that until you can visualize it without even writing anything down. So basically, this example is showing us that our original view of transpose, which is just flipping it, so flipping it along this diagonal, flipping it gives us that thing flipped along that diagonal, is consistent with this more mathematical view of transpose. And so once we have transpose under our belts, it's straightforward to come to the concept of symmetric matrices. So basically, a symmetric matrix is one that if you transpose it, you've done nothing to it. You get back exactly the same matrix. So think about that flip. If we flip it, blink, it doesn't do anything. And also thinking about the concept of transpose, the way we defined it in terms of the indices, that tells us that interchanging j and I to ij does nothing. We get exactly the same thing. And this also tells us that since we're just interchanging these and they're equal to each other, a symmetric matrix must be square. And that's why when we draw the diagonal and then grab the edges or the corners of that diagonal and flip it, it doesn't do anything. It has, in order for that to at least have a chance, it has to be square. So there's a symmetric matrix. I had alluded to symmetry earlier without formally defining it. We draw a diagonal down here. This element must be equal to that element. That's consistent with this idea. It's consistent with flipping it along this axis and not having anything happen. So here's a question. I'll just leave this for you to ponder and determine. If D is a diagonal matrix, is it symmetric? Well, you should be able to figure that out. We also know that the inverse of a symmetric matrix is also symmetric. So let's see if we can check this. So A inverse transpose, we know that we can interchange the transpose and the inverse. Therefore, since A is symmetric, we can replace A transpose by A. And notice that we now have shown that the transpose of A inverse is equal to A inverse. Therefore, A inverse is symmetric. So here's something that crops up an awful lot in engineering problems. If we take any matrix R, it doesn't have to be symmetric, and multiply it by its transpose, we get a symmetric matrix. So for any matrix R, even if it's not square, even it's rectangular, if you multiply R transpose times R, or for that matter, R times R transpose, if it works that way, it will automatically produce a square symmetric matrix. So let's prove that, not formally, but informally. So we've got R transpose times R, and we're going to take the transpose of this. So if this thing is actually symmetric, if the result R transpose R is symmetric, we should be able to show that this transpose can be removed. and maintain equality. Well, let's apply our result. We've got a product of two things, so we interchange. Now notice why we've got these things color-coded here. So we're going to interchange, so the blue R comes over here and gets transposed. The red R transpose comes over here and gets transposed. But transpose of transpose, it undoes, right? Flip and flip again, and you're right back. So then we have that. But look what we just showed. The transpose of R transpose R is equal to R transpose R. Therefore, R transpose R is symmetric, and it's pretty easy for you to verify that it's square. The matrix R transpose is also symmetric, and you can do a similar verification that that will work and that it will be symmetric. Now, is R transpose R equal to R transpose? Well, not in general. So here's R, there's R transpose. If we multiply out R transpose, we get a 2 by 2. If we get R transpose times R, we get a 3 by 3. What about if R is square? How about that case? See if you can figure that one out. So in this case, they're different. Both of them are symmetric, but they are different. So in a lot of science and engineering problems that start off with some sort of rectangular matrix being part of the problem, you almost always end up with one or the other of these, or sometimes both. So later in the course, we'll talk about a problem called least squares, which you've probably heard a reference to that at some point. And we'll see this show up in that. So here's a question. Why are the diagonal elements of these two R transpose and R transpose R, why are they always positive? I'll leave that also for you to play around with and see if you can figure out, at least with some examples. And here's some good news. If we've got a symmetric matrix that we're trying to solve system of equations for that matrix by elimination, we can do this with half the work. So remember, A is equal to LDU. Well, there's our A is equal to LDU for, that's LU for the symmetric case. Now we expand it out into LDU. So here's one of the useful things of doing the LDU instead. We've taken this matrix and split it out into this. But notice what ends up happening. I've got my L, I've got my U. Look at them. They are just transposes of each other. So the LU decomposition doesn't show explicitly the symmetry of the problem. But the LDU, it shows up explicitly. And that means that we really only have to find the U or the L. And remember, going halfway through the problem gives us the U, and then we can find the D from that. Then we can figure out what the L is by just transposing the U. So there's that example. So when A is symmetric, the usual form, which is, or the general form, LDU, just becomes LDL transpose. So very simple to find. And so this works when we have no row exchanges. So then our U is exactly L transpose. So there are some benefits of this. Remember, we saw that the amount of computation we have to do is on the order of n cubed over 3. Well, now we only have to do half the work because everything is symmetric. We don't need to find the U explicitly, we can just work with the L. And we only have to store half of the amount of stuff that we stored before. So these are the important things in computer work to make things very efficient. We can fit things into half the memory, and we can do it with half the amount of computations. So let's revisit permutation matrices. So with permutation, this idea of transpose comes in real handy. So let's take a look at an example here. So if we're talking about 3x3 permutations, so there's only 6 different permutation matrices for the 3x3 case. And here they are. I've not put the zeros into the positions where they need to be, and it actually helps you see the structure a little bit better. So there's 2 more, and there's 2 more after that. And you'll notice that I'm really just writing these last 2 in terms of permutations or multiplication of 2 of the previous. So I've got P21 times P32, and then just the reverse of that. So in general, and I think it's pretty obvious, any permutation matrix, or let me say it this way, any permutation matrix can be formed through the product of 2 other permutations. I think that's pretty obvious. If I use one permutation to arrange or rearrange, and then I further rearrange, that's just some other permutation. So that's pretty straightforward. So as we've seen, a permutation matrix is just the rows of the identity matrix reordered. And I think you can puzzle out that there must be n factorial different permutation matrices of order n. So n with an exclamation point after it is n factorial. So I think you've seen that before. And that just means multiply all the integers out to n. So you have 1 times 2 times 3 all the way out to times n. And that thing grows pretty fast. By the time we hit 5 factorial, we're already up to 120. Now, interesting thing, important concept. The inverse of a permutation matrix is also a permutation matrix. That makes complete sense, right? I make a new matrix by just changing around its order of rows. Well, to undo those, I just have to reorder them, and so that's just a permutation. But this is even more important. The inverse of a given permutation matrix is just the transpose of that permutation matrix. That's pretty remarkable. So when we start off with symmetric matrices, we saw that we ended up with LDL transpose. Now sometimes, we haven't really talked about this, but sometimes everything, well, let me say it this way. Everything we've talked about so far has said we do this LU decomposition without, for the case where we don't need any permutations. Sometimes, in order to make it work, as we've seen for elimination, we need to include the effect of permutations. So we're going to focus on applying a permutation to A first, and then on that being able to decompose that into LU. So so this is LU factorization with row exchanges. So what we've been looking at so far is that we've just been looking at a whole stream of eliminations, but with no permutations needed. And we've always had to say, except no row exchanges. But suppose we end up having to do a row exchange somewhere in there, a permutation. And maybe we have to do a whole bunch of them. So we've got a bunch of inverted permutations in there, which remember are just transposes. But what we want to do is kind of factor those all out, and it's possible to pull those all out into a single permutation matrix, P. And so let's look at two different ways to think about this. So we've got a single permutation matrix P, and we can apply that to A first. And then once we've interchanged the rows of A, then we can get an appropriate LU decomposition. Or we can wait until after the elimination, and then our pivot rows are in some odd order, and then we permute those with some matrix P1. So we're going to concentrate on the first approach here, because that's really the more common way to do this. So if our A is invertible, but we can't just charge ahead with an LU decomposition, we can find some permutation P that will put its rows in the right order, that will end up having the elimination not fail with a temporary failure. So that would result in finding some permutation matrix P that we pre-multiply by A. Then we have the form that we can do in LU. And in order to do this, we have to have a full set of pivots after the row exchanges. That's what it means to have A be invertible. Now, we're not going to deal with this too much in this course, by hand anyway. I just introduced this just so that you're aware of this. So we'll let the computers do this, and by hand we won't worry about dealing with permutations. So let's take a look at an example. So here's our A matrix. Here's a given permutation matrix. We're not going to worry too much about how we got that, but you could figure out why we needed that to avoid a temporary failure. And so when we apply that to A, we get this result, and we see we've lost our symmetry. So now we want to ask the question, can we kind of regain symmetry by post-multiplying by some permutation Q? And if you think carefully about this, you can kind of figure out what you need. And in fact, you can figure out that what you need is actually the transpose of P. So if you look at P applied from the left, transpose P applied to the right, you can verify that that is true. So let's take a look at this. We need to put the 2 back on the diagonal. So column 2 of the product PA, we got to move it back to position of column 1. And column 3 must move to column 2, and column 1 must move to column 3. So that's just looking at this and saying, what do I need to do? So let's see. We need to put the 2 back on the diagonal. So that was this. Now, they're not going to be in the same order as before, but this 2 was on the diagonal. And so now we need to move it over there. So column 2 must move to column 1. That's what I just indicated. Column 3 must move to column 2. So if we do that, that puts this 3 back on the diagonal. And then finally, column 1 must move to column 3. So so 1 was on the diagonal. It's sitting down here now. So this must move over here. So column 1 moves to column 3. So if you look at that, that's what leads to this permutation. So now we apply that, and we get not only the original things on the diagonal, but in a different order. But look, we get symmetry again. We've got symmetry there, we've got symmetry there, we've got symmetry there. So PAQ gets us back to the symmetry that we needed. So the matrix Q, as we see, is just the transpose of P. And this this will always recover the symmetry. And you can kind of puzzle out why that must be true. We've got a permutation, a symmetric matrix, and the reverse permutation. And we also know that really this is playing the role of inverse, but we've already seen that for permutations, inverse is just the transpose. All right, so here's our given matrix. Find the symmetric factorization LDL of this and figure out if this A is invertible. So I'll give you a chance to give that a shot. Give it a shot and then come back to the video and see how we really do it. Maybe you got it. All right, hopefully you're back now. So what we want to do is eliminate the pivots, or eliminate below the pivots. So here's our original. And so we've got 4, 5, 4 and 5 we want to eliminate. So we eliminated those. Then we want to eliminate the 14. We eliminate that, and we end up getting something that looks like that. So that's our U matrix. And we figure we can see what our multipliers would be. And so those go into our D matrix. And so we divide the rows of U by those. And our LT should automatically appear. So this is one that doesn't require permutation, so it was an easy one to do. So there's our final answer. So like I said, by hand, I'm not going to ask you to worry about dealing with the permutations. So if I ask you to do LDL transpose for a symmetric matrix, it won't require any permutations. But you should at least be familiar with the idea that you can come up with the generalization or the trick of using permutations to take care of all that. And we see that this is invertible because our D matrix in the middle has all non-zero values. So it has 3 pivots. So definitely invertible. And these decompositions are nice to be able to compute the inverse of a given matrix. So that's one place where they're used. But they're also used to kind of factor matrices so that we can implement more efficiently different algorithms and so forth. So that's the end of this set of notes, and I'll see you in the next video.